Alright, in this example we are going to find the internal shear and bending moment of a beam at a specific point. And when you do that, you're almost exclusively going to use an equilibrium approach to that. And we'll talk about what that means here in just a second. Right? So here we got a beam that is 9 foot long between the supports, a pin support and a roller support. That's what makes it simple. It's not simple because it's easy. It's simple because we have simple support conditions, pin and roller. This beam has two 3-foot overhangs, so little cantilever segments. The loading is actually kind of complex. We got a uniformly distributed load at 8 kips per foot. The right overhang at its end has a 17 kip applied load, and then at the left end we have a 35 kip foot force couple that is applied. And in response to those, we have reactions at the supports that would probably be columns. Right? That's what that probably represents. That would be 26.4 kips on the left and 62.6 kips on the right. We've been asked to find the moment at 3 foot to the right of A, and although it's not marked, it's sort of implied that the reaction at the left is point A, so we're 3 foot over to that. So what we're going to do is we're going to go cut a free body diagram 3 foot over from that reaction. Right? And when we do that, note we've got to put the applied moment of 35 kip foot in there. We've got the reaction of 26.4, but we must, and once again must, show the portion of the distributed load that we're cutting through. We are not going to lump all the force here. That would not be statically equivalent internally. It would be statically equivalent to do that for the reactions, but not for the internal. We must include this portion of the distributed load that is in our cut, and that's what you see down here. Right? Now when we go to show the internal effects, we want to use the positive sign convention that we've got shown over here to the right. Right? There's going to be multiple sign conventions running around here. You have the global system that you might think of as the Cartesian coordinate system. Right? And then you have the system that you might use in your equations down there briefly. I don't want you to see those yet. And we have the internal sign convention. 3 different sign conventions that you have to keep track of. Right? And so I keep this little drawing around for all the time here. The only one that I remember easily is positive bending moment, because positive makes me happy, and then I usually smile when I'm happy, so therefore the beam curves concave up, and these are the moments that would go along with that. Usually people like to use the axial forces as being tension, and that's positive, they say. And then the shear, I have a hard time remembering. It's up on the left, downwards on the right. I have other devices that we'll learn about in later modules to reverse engineer what that positive direction is, but I sometimes have to think very carefully about what that is and go back to a drawing like this. Right? So that's why you see over here the shear at a point. I got V sub A going downwards. I've got M sub A showing, oh, this is the right hand exposed face, so it would be the counterclockwise one. How do I know it's right hand exposed face? Well, there's the solid, and the solid is to the left. The outward normal is to the right. That's the axial force, so we're on the right hand side. That's what makes that the M going in the positive counterclockwise fashion, M sub A, right? A because that's the point. We're not, yay, that really shouldn't be A, that should be O. There we go, that makes a little more sense. We're at point O here, right? 3 foot to the right of A. Means I'm going to have to make some other labeling changes here shortly, right? So there's a proper free body diagram. Got all the loads, we got the reaction, we have the internal forces. Okay, so now it's time to go do equilibrium. The x direction is easy. There's only one force in the x direction, so sum of force in the x equals n0 has to be equal to 0. Sum of forces in the y, 26.4 going up. I took for the equation upwards positive, minus 8 kips per foot times 3 feet. That's going downwards, so negative. And then the shear on the free body diagram is going downwards. Even though it's positive internal shear, it's negative in the equation. Right? You got to keep those things separate. And so minus V0 equals, and then all of that equals 0. And so we find out that the internal shear is a positive 2.4 kips. Right? That positive sign, I go back and interpret the direction based upon, do I have a left-hand exposed face or a right-hand exposed face? Right? And then the moment goes similarly, and I need to slightly adjust my symbols here. Well, some moments about that point 0, we get 35 kip foot is going opposite of the sign convention. You must label your sign convention for the equation, not the same as the internal sign convention, right? So minus 35 kip foot there, minus 26.4 kip reaction times the 3 foot moment arm, plus the 8 kips per foot times 3 foot, that's 24 total kips, acting at the centroid of the little partial one, and then times this moment arm over to the point of interest. There's your 1.5 feet, plus the M0 is all equal to 0. And that's how we then solve for that our moment at that point, 3 foot to the right of A, is 78.2 kip foot. Right? I want to go back now and just talk about a couple of things real quick. One, I didn't include the shear because even though I drew it off to the side, it is going right parallel, right on the cut surface. Right? So there is no moment arm there. Right? So I don't include that. And of course N0 goes through that longitudinal axis. It doesn't create a moment on the cross section. And so the only moment there internally is the M0. I also want to point out again, you can't put the total load right here at the beam and turn in the centroid of that rectangle and turn it into a single concentrated force. None of that distributed load would have shown up in this equation. None of that would have been there. So your shear would have been wrong. You would have said shear was equal to 26.4. It's not. It's 2.4. And your moment would have been entirely wrong. You would have missed this final 36, and you would have over-predicted the moment in this case by quite a lot. So you've got to be careful on how you create these free body diagrams, and you're thinking about how to work with them. That's why you never see me replace a distributive force with a single concentrated one, so I don't make those mistakes. I keep them. Now I'll put a little dot where the centroid is, where it's acting equivalently, but that's all I will do.